Welcome back, everyone, to this section of the course on logistic regression. We've just explored how to use linear regression and its many variations, such as lasso regression and ridge regression, to predict a continuous label. But how can we predict a categorical label? For this section, the answer will be logistic regression. Keep in mind, in the future, we'll be exploring a lot more than just logistic and linear regression to predict things like categorical labels and continuous labels. Also, remember to not be confused by the use of the term regression in the name logistic regression. To be perfectly clear, logistic regression is actually a classification algorithm designed to predict categorical target labels. So in this section of the course, we'll first discuss how to transform the linear regression algorithm to logistic regression using the sigmoid function, otherwise known as the logistic function. So we'll see the direct transformation going from linear regression for continuous labels to logistic regression for categorical labels. Then we'll discuss the mathematical theory behind logistic regression, including how to solve its gradient descent problem. Then we'll switch gears to Python and scikit-learn for a simple implementation of logistic regression for classification. Afterwards, we'll talk about how to interpret the results of logistic regression, specifically things like the odds ratio and the logistic regression coefficients. Afterwards, we'll have a larger discussion on classification metrics that will apply not just to logistic regression, but any classification problem, things like accuracy, precision, recall, and we'll also discuss ROC curves, otherwise known as receiver operator characteristic curves. Then we'll go back to Python and show you how to solve multi-class classification with logistic regression, multi-class being more than just two categories. Then we'll test all your new skills with a logistic regression project exercise and also show you the solutions for that project. So let's briefly discuss logistic regression, just to give you an overview of what it can do. It essentially allows us to predict a categorical label based on historical feature data. The categorical target column means that it's two or more discrete class labels. For example, we could use a classification algorithm to predict a class or category label, such as what class an image stands for. Maybe it's class 0, a car image, class 1, a street image, or class 2, a bridge image, and so on. And if this kind of problem sounds familiar to you, it's because you may not have realized that you're actually helping Google, with its self-driving car unit, Waymo, classify historical data. Because obviously, it's really important to have already classified historical data to train an upcoming model on new data. So when you're actually filling out these CAPTCHA calls and identifying images, you are yourself labeling data for Google. So you're selecting all the images with cars. I also want you to keep in mind that theoretically, any continuous target can be converted into categories through a process known as discretization. And essentially what this does is you bucket the continuous label into categories. If we think back to the house price category that was continuous, we could say that class 0 is going to be the category of a house price between 0 and $100,000. Then class 1 is a house price above $100,000 all the way to $200,000. And then maybe class 2 is any price that's above $200,000. And here, you've converted a continuous target to three distinct categories. This is not going to be a case we imply often, but I just want you to be aware of the fact that you may see problems in the real world go from a continuous target label to a categorical one. However, typically you can't actually go the other way around unless you have the original continuous information to begin with. You should also realize that classification algorithms, not just logistic regression, also often produce a probability prediction of belonging to a class. So they don't just say, I predict class 1 or class 2, they'll actually report back the probabilities for each class for a particular data row. They may say there's a 10% probability of class 0, 85% probability of class 1, and 5% probability of class 2. So in this particular case, the model will just report back, I predict something like class 1. Maybe in this case, it's the street image. And you should keep in mind, behind the scenes, it actually has an assigned probability for each of these classes that we can easily actually grab from the algorithm as well. Also note that when it comes to our prediction y hat, since it's going to be a category, we're not going to be able to calculate a difference based off y minus y hat. We can't really say that if the true image was a car image and our model predicted a street image, we can't say car image minus street image. Or if the category was red and we predicted category blue, there's no real formula for red minus blue. So that means we'll have to need to discover a completely different set of error metrics and performance evaluation. The things we learned in the previous section, like mean absolute error, root mean squared error, etc., those actual performance error metrics will not apply for any classification problem. We need to discover different ways of evaluating our performance, such as accuracy, precision, and recall. Okay, I hope you're excited because there's a lot to learn. I'll see you at the next lecture.